Hello, welcome back. And as promised, we'll be looking at the rules of calculus, right? We'll be learning how to do differential from now on, right? So, just some basic stuff out of the way. If I have any equation like y equals to 4x squared plus 13, I don't know. So, dy over dx just means small change in y over small change in x, and the equation that this would give out is called the differential, right? The differential of this equation. And also one thing to notice is that since y equals this thing, right, you can simply substitute this thing over here. You can simply exchange them. So d of 4x squared plus 13 over dx is just the differential of 4x squared plus 13, right? So now calculus has a bunch of rules and procedures that you follow in order to get a differential or an integral, right? And the first very basic rule that we must discuss is called the power rule of differentiation. Right? And just one thing before we start, that you don't necessarily need to be that intimidated by these rules at first, because after some practice you just get used to them. They just become second nature, right? So what the power rule is, it is that for any x to the n, its differential is n multiplied by x to the power n minus 1. A lot of the people remember it as a lot of the people remember it as taking this power, dragging it down over here to the coefficient and subtracting 1 from it. Right? And for example, if we had any constant k multiplying by it and you were differentiating, what you would do is you just multiply that constant when you drag down the power. So k multiplied by n multiplied by x to the n minus 1. Right? This dot is just multiply. It's just more convenient than making a cross. Right. So let's just look at a few examples to know that you have got it down. So say a differential of 4 multiplied by x squared will be 4 multiplied by 2 multiplied by x, which is 8x, right? And say if I take something like 4x and I differentiate it, it would be, well, 4x means x has the power 1. So when I put this power over here, it becomes x multiplied by 1 multiplied by x to the power 0. And recognize that anything to the power 0 is just 1. So this is 4, right? And say if I have any constant, right? If I have any constant 4 in this case, well, 4 has, it is independent of x, right? It has x to the power 0. So when I push the x to the when I push the 0 over here, it becomes 4 multiplied by 0, and anything multiplied by 0 is just 0, right? So any differential of any constant is 0, right? That looks like a circle is 0, right? And recognize that whatever I've done here, whatever these are I'm getting over here, this is the differentiated equation of whatever was in here, right? So let us take these two examples and relate it to stuff that we already know. So y equals 4x, right? I'm sure you already know what y equals to 4x looks like. It is a straight line, something like this, whose gradient m is 4, right? For any y equals mx, we know that the m is the gradient, right? And remembering that m is just change in y over change in x, and that is what differentiating also is. It is taking small change in y over small change in x. So for any line y equals to mx, the gradient m is its change in y over change in x. And so it also makes sense that for when you differentiate for x, it gives you just the constant 4, right? This agrees with stuff that we already know about, linear equations. And if we look at something like in this case a constant, so y equals 4. Y equals 4 is, well, is just some horizontal line that is constantly at the value y equals 4, right? And we know that for any constant line, the gradient of it is 0, simply because the gradient is change in y over change in x, and if it is constantly at 4, there is no change in y, right? So the numerator is 0, and hence this is 0, right? And so this also agrees with our power rule that when you differentiate any constant, right, following this procedure, you also get 0, right? So these two examples are something that we can relate and sort of agree that the result that the power rule gives us is sort of making sense, right? And so this is what power rule is. And now I'll be talking more about, why this power rule sort of makes sense. In calculus, you might feel like these are just a bunch of laws that are being laws and rules that are being thrown at you. But know that these are rules that do indeed work, right? So for for a few more minutes, I'll be trying to convince you more loosely why the power rule sort of makes sense. Right, so let's take a look at the equation y equals x squared. Y equals x squared looks something like this, not like that, something like this, right? And y equals x squared, this is x, this is y equals x squared. I can also represent this as a square, that is a horrible square. I can represent y equals x squared as a square whose side length is x, and the y value is the area of that square, right? So for any square of side length x, its area x is x squared, and this is another way of representing y equals x squared, right? For any square whose sides are x, the area of that square is the y value, right? So for example, if I have a square whose lengths are 3, 3, right? So when x is 3, this area is 9. So when x is 3, the y value is 9, right? So now let us take a square, right, that has length x, x, and so the area is x squared. And suppose I increase my x a bit, right? So there will be some increase like this, right? I increase it by some x plus dx, right? And this will also increase by some x plus dx, right? What I've done is that I've just taken that x and I have increased it by some value dx. And remember that dx in principle is a very small change. In this case, I have made it bigger just so that we can see, but in principle, it is a very small change, right? Here I increase this much by dx and I increase this much by dx. And so the new area after I've introduced this change, the new area becomes x plus dx multiplied by x plus dx, right? Or x plus dx squared. And also remember that the original area was x squared because originally your lengths were x by x. So the area of an x by x squared would be an x by x square would be x squared, right? So if I want the change in area, what I will do is I will take the new area and subtract the original area from it. So x plus dx squared minus x squared, right? So I can represent change in area as dy. So let's expand x squared plus 2x dx plus dx squared minus x squared. Both of these cancel. Dy equals 2x dx plus dx squared. Right. Now notice that here I can take dx common. So when I take dx common and I send it over here, it becomes dy over dx is equal to 2x plus dx. Now, we know that dy over dx is the value that it would approach when as dx is approaching 0, right? As dx is getting smaller and smaller, right? So when dx is getting smaller and smaller, notice that this would essentially become smaller and smaller until it just becomes 0. And also noticing that this term has no dx in it, and so as dx is getting smaller and smaller, this won't be affected, right? So when dx is smaller and smaller, this dx is pretty insignificant and we can ignore this, right? So what we end up with is dy over dx is 2x, right? So we proved that the differential of x squared should be 2x, and we use this neat representation of a square, right? And in fact, you can extend this area further to y equals to, let's write it here, to y equals x cube. What you would do is you would take a cube down of length x by x, right? So this is a cube of length x over here, and x over here. And now the y value is actually the volume enclosed by it, right? And it's a bit hard to draw, so you would have to mainly imagine it. But imagine that I increase my x some dx value, right? Oops, by some dx value. So there will be some change over here, some change over here, and also some change over here, right? You would have to mostly imagine that there's some increase in x dx, right? And so notice that now the change in the volume, i.e. the change in x cube, would be okay. So if we look at this face over here, there would be some x squared dx, right? The x squared comes from this being multiplied by this, and there's some change dx, and so the increase in volume that I'm getting by focusing on this face is x squared dx, right? And applying the same idea to this face and then to this face right over here, I get another x squared dx and another x squared dx, right? And now I know that there is some parts of the change in volume that I am ignoring, right? For example, there would be a cube over here whose volume would be dx cube that I haven't accounted for. So there will be some values each which have either a dx squared or a dx cube, right? So it could be something like it could be something like x times dx squared, but every term over here will have a dx that has either power 2 or power 3, right? So this was my dy. So when I take my dx common, notice how it becomes dy over dx, right? And every term that initially had a dx would now be free of a dx. So x squared plus x squared plus x squared plus some values, each of which still have a dx. So something like x dx or dx squared or something, right? And applying the same idea, how since dx is approaching 0, these values would also become more and more significant, right? So essentially these terms which don't have a dx, simply because it got factored out over here, now these terms will form the bulk of the new volume. So dy over dx would now turn out to be 3x squared, right? So we also proved that the differential of x cubed should be 3x squared, right? And if this is sort of troubling you that, why are we sort of ignoring these values, just remember that this is an approximation that gets better and better as we take smaller and smaller changes in x as our dx approaches 0, right? So for any x to the n, right? We show for any x to the n, when you differentiate it, it becomes n multiplied by x to the n minus 1, right? We prove this when n is 0, i.e. when it is a constant. We prove this when n is 1, right? We also took a look at why when n is 2 and when n is 3, it sort of makes sense. So when you see a pattern, when you look at it in a row, you would see a pattern that for any x to the n, when you differentiate it, it is just n multiplied by x to the n minus 1, right? And I know this is not a complete proof of it, but if you are eager for a proof, you can extend the idea that when you expand x to x plus dx to the power n minus x to the power n, and remembering that once, okay, so this is dy, remembering that once you factor out the dx, only those terms that are independent of a dx will be the values that will matter, right? So if you're really eager for some sort of a proof from this knowledge that you have right now, or you might have from before too, but from the things that we have talked about, you can work out its proof if you really want to. And sure, go ahead, it's actually a neat enough proof. It also uses the idea of permutations. Right. So that's it for the power rule for now. Bye bye.